All right, let's look at that problem in op amps, and then we'll begin chapter 4 after. Okay, so as promised, let's tackle this problem. So this this amplifier circuit has multiple resistors in the feedback path, right? Typical inverting amplifier has only one resistor. Question being asked here is to derive the gain for this circuit. So AV, derive AV for the circuit. The gain for the circuit AV, of course, is the ratio of the output voltage to the input voltage, V out or V in. Okay, output voltage, V out or V in. So let's go to the first usual steps. First, we want to verify whether negative feedback is present. So we see here that output is fed back into the inverting terminal. So yes, negative feedback is present. Right, negative feedback is present. That means that the input is being forced to go towards 0. So VI and II can be assumed 0 for the purposes of analysis. Okay, we can assume VI and II to be equal to 0 for the purposes of analysis. All right. Then the non-inverting terminal is connected to ground. If the non-inverting terminal is connected to ground, then we can say the other terminal, which is the inverting terminal, is at virtual ground from the virtual short concept. So again, negative feedback is present. So input is being forced to go towards 0. So we can assume VI and II are equal to 0. And then non-inverting terminal is ground. So we can say the inverting terminal is at virtual ground. Okay. So from this point on, we can apply Ohm's law, KVL, KCL in any order we choose to determine an equation for V out over V in. Okay. So let's take a look. Physically, these terminals are all connected to ground, and so is this. Okay. So these three are connected to ground. So I'm going to place a wire right there. And then another one right there. This is all connected together. Okay. And then, of course, if physically these three are connected together, that means this one is also connected. And this is also connected virtually. But that'll come later in the problem. So now our analysis techniques are Ohm's law, KVL, KCL. These are the only three techniques we have, right? So our goal is to write equations using KCL and KVL, and then somehow obtain V out and V in those equations, so we can rearrange the terms and obtain AV. That's what we're going to do. So we're going to start on this end, and we're going to move towards this end while we're writing our equations to get to V out. And once we have V out and V in the exact same equation, we can rearrange those terms to obtain V out or V in. Okay, so let's begin. This is noted as node number 1. This here is node number 2, and this is node 3. Okay, node 1, 2, and 3. We have I1 entering, coming from V in, and then splits into I2 and II. Okay, but II from our assumption is equal to 0. If II is equal to 0, I can write an expression for I1 as I1 equals I2. We apply KCL at node 1 to generate equation. we obtain I1 as equal to I2 plus II, but because II is being forced to 0, I can write I1 is equal to I2. Current's going straight up right there. I1 is equal to I2. That's the first step. Okay. Then if you apply KCL at 2, I have I2 entering, I3 entering, and I4 leaving. These current directions were already given to us. Okay. These current directions already given to us, but let's say you were analyzing any circuit and you choose the opposite direction, it won't make a difference to your analysis. Okay. As engineers, if this was something completely unknown, I would begin by just assuming any current direction based on some logical rules and laws of physics, and they would simply proceed with my analysis. If that didn't give me the right answer, I would change my assumptions and I would proceed with the analysis again. Okay, I would redo my analysis. In this case, the directions are given to us, so it makes it easier. Once you apply KCL at 2, I get I2 plus I3 is I4. And again, keep our goal in mind. We want to go from here, V in to V out. Okay. We could also start from here and go towards V in. It doesn't really matter. We can write the output equations first and then move steadily towards the input, or we write our input equations first as we move towards the output. Again, doesn't really matter. All right, so now let's take a look at I1. I1 can be described from Ohm's law as the voltage across R1 divided by R1. So I can write VR1 or R1, right? From Ohm's law, I1 is VR1 over R1. And VR1, the resistor voltage, can be described in terms of the node voltages at both ends of that resistor. And that would be V in here and V minus here, or VI at the other end. Okay. V in minus V minus. V minus is the voltage at the voltage at the inverting terminal. But that voltage would be equal to 0 because we are assuming virtual ground. Again, I1 from Ohm's law is VR1 over R1. And VR1 we can describe as the difference in the two node voltages, V in and V minus. And because V minus is 0 volts from virtual ground, I can write I1 is equal to V in over R1. Let's take a pause. Let me know if you have any questions. So far, so good. Okay. Then, how about I2 and I3? Same thing from Ohm's law. I2 is VR2 over R2. I3 is VR3 over R3. Okay. Now here's the thing. We want to get V in into these equations in the mix. So we are going to redraw the circuit and look at it in just a little different. This node right here is at virtual ground, right? And this is at physical ground. So I can create a loop that goes from here to here. Okay. Again, node 1 is at virtual ground. So I can create a loop that covers both R2 and R3. And if that's the case, I can redraw it like this, where R3 is physically grounded and R2 is virtually grounded. And that creates a parallel connection. So R3 would be in parallel with R2 because they are connected here at this end at the top, and they're also connected at the bottom end. And again, this is for the purposes of analysis, okay? This is for the purposes of analysis. In real life, it just turns out that this works. The op-amp works in exactly the manner that we're describing. Okay, so this has all been verified. Does this make sense? R3 is physically connected to ground. R2 is virtually connected to ground. So we treat R2 and R3 in parallel. Okay. Yes. So this is given in the circuit. So question being asked is, how do we know it's physical and virtual? So this is already given to us, meaning this is physically connected to ground. And this right here, this node 1, is because of the virtual short or virtual ground concept. So virtual short. You have to think in terms of like when this was a completely unknown circuit. So decades ago, this was completely unknown. Engineers are trying to analyze this circuit. Now, when you're trying to analyze an unknown system, we always have to make certain assumptions. So whoever did that analysis long time ago certainly made lots of assumptions, and this is the assumption that turned out to be true. Okay, so we already know this for a fact that this works, but again, as students, we are approaching as if it's a new thing, but in reality, this has already been done in the past, right? When we learn about something, when I learned it as a student 30 years ago, this was still the case. This was already solved. And so when I, as a student, learned this, someone already had made multiple assumptions in the past. Most of those assumptions didn't work. Some of them did, and this is the one that did work. Okay. So trying to figure out the analysis, we can still do it. We can make the other assumptions and try to analyze the circuit, and we will arrive at the same conclusion that those assumptions didn't work, and then we'd be forced to come back to these, and these will work. Okay. All right. So here again, R2 and R3 are in parallel, and because they're in parallel, I can state that the voltage across R3 and voltage across R2 is the same. Okay. And the currents are moving in the exact same direction. So the voltage polarities are also the same. So VR2 is the same as VR3. And there's a purpose to this. Remember, I said we are trying to incorporate V in into our equations for V out, right? So we are going from V in to I1 to I2 to I3 and I4 and then to V out. So if we take this loop, I can write I3 is equal to VR3 over R3. Then I can say VR3 is the same as VR2. And I can plug in VR2 as I2 times R2. And I2 is equal to I1. So I plug in I1 in there. So I'm moving back. I'm moving from I3 to VR3 to VR2 to I1. And from I1, I can move to V in. Okay, so I'm moving back one step at a time. And now I have V in my equation or expression for I3. Does that make sense? Let's take a pause while you think over that and let me know if you have any questions. This is the most important part because this is where the assumption comes into the picture. questions? Everybody understood? So you'd be able to come up here and explain, or you'd be able to take a pop quiz at least. I see some nods. It's a shame. Sorry. Yeah, you want one? How about for extra credit? Too late. All right. Anyway, jokes apart. Does this make sense? We write an equation for I3. I3 is VR3 over R3. We say R2 and R3 are in parallel because of virtual ground. So VR3 can be replaced with VR2. VR2 from Ohm's law can be defined as the product of I2 and R2. I2 is the same current as I1. And then I1 we described earlier as V in over R1. So now we have an expression for I3, which incorporates the input voltage V in. We have steadily moved towards our output. Okay, we are halfway there. V in has moved halfway to here. Now we need to bring V out also in here. And for that, we look at the output loop. So if you look at the output loop right here, I can apply KCL. Sorry, KCL at 2, which gave me I2 plus I3 is equal to I4. Okay, KCL at 2 gave me I2 plus I3 is equal to I4. One current coming in, second current coming in, a third current going out. Okay, I2 plus I3 is equal to I4. And we already obtained an equation for I3, which has V in. So now we need to write expressions for I4, which has V out. So if we plug the equations we derived here, equation 3 and equation 1, we plug both of these in equation 2. We obtain this expression. I4 is I1 V in over R1 plus I3. And so we can get V in times 1 over R1 plus R2 over R1 times R3. We still don't have V out. We still don't have V out. So now we look at the output loop. And the output side, we have these three resistors, R3, R4, and RL, the load resistor. If you apply KVL, the sum of the three resistors should give us 0. We take V out on one side of the expression. So we get minus VR3 plus VR4. VR3 is there, VR4 is there. We plug in expressions for I3 and I4. And then all we have to do is plug in the equations for I3 and I4 in that equation, and we have both V out and V in the same equation, which was the goal. The purpose of doing this analysis is to find AV. AV is the ratio of V out to V in. So somehow we have to write multiple equations that incorporate both V out and V in. And the end goal is, of course, to obtain V out and V in the same expression. Then we rearrange the terms. So we have V out over V in and the rest of the terms on the other side, which is right here. So we obtain an expression for V out over V in. All right, let's take a pause. Let me know if you have any questions. Do the steps make sense? I'll scroll up. Any questions? So I'll do a recap. We have multiple resistors in the feedback path. We see it's an inverting amplifier because V in is going into the inverting terminal, and it has negative feedback. So we can make our usual assumptions. We want to derive an expression for V out or V in. We can start on the left-hand side and move steadily towards the output, or we can start at the output and move steadily towards the input. Okay. We apply our usual analysis techniques, Ohm's law, KVL, KCL to generate multiple equations. We applied first KCL at 1, then at 2, and then at 3. We obtain expressions of V in and V out in the same equation. Rearrange the terms, and we obtain the gain equation as shown right here. Now, if all resistors had the same value, let's say you're performing an experiment in the lab, all you had were 1 kilo ohm resistors and you needed a gain of 3. Well, you could connect 3 resistors in series and obtain 3 kilo ohms in the feedback path, and you would collect 1 kilo ohm at the input, and you'd obtain a gain of 3, right? Easy enough to do. So you plug 1 kilo ohm right here in that expression, your gain is 3. But if you want something large as your gain, right? Let's say your input signal is very small, 10 millivolts, 50 millivolts, very small input signal. You want a gain of like hundreds. If we use a large resistor in the feedback path, the current through there is going to be small, so the circuit won't work. I mean, theoretically it will work, but practically speaking, it might not work. If you want a gain of 100 and you plug in a gain of 100K, I mean, a resistor of 100 kilo ohms in the feedback path, the current will be very small. Your theoretical gain would be 100, but your circuit may not work as intended. Okay, so look at this. You have standard resistor values, 1 kilo ohm and 10 kilo ohms. You plug in R1 and R3 as 1K and R2 and R4 as 10 kilo ohms, and your resulting gain is 120. Okay. Simply by configuring 3 resistors in the feedback path, your gain has now changed. It's easy to obtain a large gain value with only 3 resistors. You could also possibly design something like this. The analysis would work the same way. You would write KCL at every step, and you move from one step to the next until you have V out and V in the same expression. Okay. All right, questions? Yes. So we didn't apply KCL, but we did. It's like right here. If we needed to, we could have, but there was no need to. So here, note 3. Okay, so one other problem in this chapter was 13.21, which I have here. There was an error in the solution, so I'm reworking the solutions. So I won't be able to cover this right now in class. I'll either create a video or I'll just copy my annotations in here with the solution. So this is basically a non-inverting summing amplifier, right? A non-inverting summing amplifier. So the output gain for this should be 1 plus RF over Rn times VA plus VB. That should be the gain equation. And there was a minor miscalculation, so I need to redo that. So I'll do this outside of class. For now, let's turn our attention over to active filters. And we looked at active low pass filter. Let's look at active high pass. Okay. So capacitor and a resistor in series functions as a filter. If this is our input, F in, the output across the capacitor is a low pass filter. The output across the resistor is a high pass filter, right? So in the low pass filter, we had the capacitor in the feedback path right here. Oh, in the feedback path right here. Here, it's in the input path. So as the frequency increases and tends towards infinity, capacitor behaves like a short circuit. V in is allowed to pass through. As F tends towards 0, capacitor behaves like an open circuit. V in is blocked. Hence, low frequencies are allowed to pass through. Hence, it's a low pass. Low frequencies are blocked. High frequencies are passed through. Hence, high pass filter. It functions as a high pass filter. Okay. Again, passive filters simply have a resistor and capacitor. They do not amplify the incoming signal. These are found mostly inside speaker boxes, like passive speakers, like the ones that we have here in the room. Those are passive filters. And then active filters found inside electronic processing units or audio processing units. And those have gain functions in their filters. They perform filtering and amplification at the same time. There's one more kind of filter we can obtain by connecting these in series. It's known as cascaded bandpass filter. This is a low pass, active low pass filter, active high pass filter. The gain for both is 1. And here is simply a amplifier gain of RF over Rin. Yes. So I was gonna say, has anyone ever used a boombox with mechanical sliders for graphic equalizers, or even any kind of audio system with mechanical sliders? Anyone remember those? Those are basically nothing but active filters. So here, a low pass filter is going to permit low frequencies to pass through, and high frequencies are blocked, right? A high pass filter allows high frequencies to pass through, and low frequencies are blocked. So the output here, we obtain a band of frequencies that are allowed to pass through, whereas everything else is blocked. So a graphic equalizer is a circuit, is an electronic circuit that filters out certain frequencies and only allows certain frequencies to pass through. So if you look at a graphic equalizer, whether you have a manual one, whether it's a digital one, it'll always state the range of frequencies for every single slider. Even the bass and treble and mid controls that you might see on any audio amplifier or a mixer will have a range of frequencies. When we adjust the dial for the bass, we are amplifying the low frequencies. When we adjust the dial for the treble, we're amplifying the high frequencies. Okay, each one of those is an active filter. So each slider on a graphic equalizer amplifies or filters out a certain band of frequencies. And when you move the slider up, we are increasing the gain for those frequencies. So it's not only filtering, it's also amplifying your signal. And typically, graphic equalizers, the settings were this, the sliders would be set kind of like this. This would amplify the high frequencies. Yes. So it's digital system, but it does the same function. Yeah. So everything nowadays is digital. We can download an app on our phones, on our smartphones, and we can filter out frequencies using software. Yes. Yes, that is correct. That is correct. This question being asked was, it only allows certain frequencies and then only amplifies certain frequencies. The answer is yes. It filters out those frequencies, also amplifies those certain frequencies. At the front end of every wireless device would be an active filter. So if you hold up your phone right now, there's multiple signals, AT&T, Verizon, and T-Mobile. Those are the three main providers. All other networks run off these three major networks. These three are the only ones that have their own networks, okay? So if you have a Verizon phone, they don't want AT&T signals to come in through. They lock it down. You cannot use your phone on anyone else's network. How are they doing that? Well, filtering is one of the options. You have a filter at the front end that only allows Verizon signal to come in, and those signals are amplified, the other signals are blocked. An AT&T phone, again, locking down a phone on a network can take many different forms, but just a device by itself, there's a filter in the front end. And so it only allows certain frequencies to come through, everything else is blocked. Okay. All right, so with that, we'll say this chapter has come to an end. From now on until the end of this quarter, we'll be working on something completely different to what we have done so far. And that, the first step there is logic circuits. Logic circuits is basically unlike anything that we have discussed so far. So far we're working with analog signals, right? So let's first take a look at the difference between analog and digital, okay? Analog and digital. So I just said now we're working with logic design. It's technically it's digital design or digital circuits. Digital circuits deal with digital signals. And the difference between a digital and analog signal is shown right here. An analog signal can take an infinite number of values at any given point in time. Okay, so it might have a different value at any given point in time, but within the range or within a specific time range, it can have infinite number of values. Okay, a digital signal, on the other hand, has a fixed value. Okay, typically inside a system, there's only two values that a digital system can take. Okay, high and low, and that's it. High and low. Okay, and the system is known as a digital logic system. So these values are known as logic high and logic low. An example can be a light switch or a fan switch. Okay, a light switch only has two positions, on or off, only two states. Similarly, a digital system only has two states, on or off. Only two values possible. Now, however, if you have a light dimmer is a dial that you just turn manually, and that can take on any value depending on the position of the dial. That would be an analog signal versus a switch that is only on or off. Okay. So again, digital signal has only two values. Analog signal has infinite possible values. One of the advantages of a digital signal versus analog is that it has better noise rejection capability. So if this is an analog signal, any unwanted signal that comes up is considered as noise. Anyone ever listen to AM or FM radio stations in their vehicles? If you pass by on the street or on the highway, you might be picking up two different radio signals, and you'd hear two different radio stations at the same time in your car. Or have that happen, right? So if you're trying to listen to 101.7 FM and you're passing by, depends on the location, you might also pick up 101.9, right? That is noise. We don't want that signal to come in there. So any unwanted signal is basically noise, right? So an analog signal, that noise would be added on. Okay, so the value of the signal at any given point in time could change. And that noise could be added on to that signal, or it could subtract from our desired signal, depending on the phase, depending on the value, right? It could add on to our desired signal, or it could subtract from our desired signal. With the digital signal, it's different. Digital signal has one single fixed value. So any noise signal that comes in is still considered to be on within a certain tolerance. But noise signal that affects the level of a digital signal may or may not end up altering your output. With an analog signal, it will. The digital signal, if the system is well designed, then it will not affect your output. Your system is still considered to be on or off. So it's very good at rejecting noise signals. Okay. So digital signal, or a digital system rather, is good at rejecting noise signals. Okay. So if it's only two, our digital signal can be represented as, I'm going to come back to this. Digital signal can be represented as either being on or off, meaning presence or absence of voltage. Okay. If voltage is present, it's on. If voltage is absent, it's off. Only two states or two values. It's a binary choice. Only two possible states, either on or off, meaning either 0 or 1. And thus, we have the binary number system. Machines, devices, meaning our transistors, diodes, FETs, the devices that we use to build our circuits, these machines can only understand presence of voltage or absence of voltage. So if you want to communicate, if you want to communicate with the machines, if we want to design systems, we need to understand their language. And that is where the binary number system comes into the picture. So how many of you understand the binary number system? Got a very tall hand being raised, only one. Do you all understand this? Okay, that's good. In the binary number system, 10 represents decimal 2. And I have another meme, for, well, not a meme, but a comic panel in the next one. It's just funny. I don't know of an elementary school kid who knows binary, but if he does, 100 is absolutely right. It represents 4 in the binary number system. All right, so let's go back to our on and off. Okay, so as we said, it's good at rejecting noise signals, right? So if you have a digital signal, we are trying to transmit from point A to point B, right? You're trying to transmit data from point A to point B. It picks up some noise along the way, right? So at some points, our data is supposed to be on, meaning it's supposed to have a value of 1. This is actually, it doesn't matter what this is. This is the voltage level. So it's supposed to have a logic value of 1, logic high. But let's say a noise signal arrives and drops the level. Let's say this is 5 volts. Okay, logic high is 5 volts. It drops the level down to here. That's the signal. So now, do you still consider this to be high or not? As an engineer, if you're designing a system, then yes. Let's say this drops down to like, I don't know, 4.5 volts or 4.75, 4.25. It's a random number, 4.5, because of some noise, right? So we know which environment our system is going to be used. So we know what kind of voltages level it could drop to potentially. So we build that tolerance into our system, meaning even if some noise signal arrives and it drops our level down to, to a certain level, we would still accept that level as logic 1. So if we send 1 from point A at point B, it's still recognized as logic 1. And thus, it is able to reject noise. Does that make sense to everyone? So in that way, digital system is better at noise rejection versus an analog system. The same thing can be applied to logic 0. If you have logic 0 right here, meaning a logic low, and some noise signal arise that raises this level. Instead of being 0, it could be considered as 1. But because it's digital, even though it's supposed to be 0 volts and it raised up to like 0.3, 0.4, 0.5 volts, at the receiving end, the system still recognizes that this is logic 0. And if it recognizes logic 0, it's now rejecting any noise signals. So that is known as the noise margin, NM, noise margin. For logic low, it is termed as noise margin L, NML. For logic high, it is labeled as NMH, NMH. Okay, anywhere in the middle is the undefined region. Okay, undefined region. All right, so yes. We try to design systems so that it doesn't go into that undefined region, but it does happen in the early days of digital TV transmission. And you can still pick up, like if you have rabbit ear antennas and you connect it to your television, you can pick up free over-the-air televisions. If the signal is fuzzy, in the analog systems, if you have seen, you could see a picture, but there'd be horizontal lines running through it. With digital transmission, if there's missing data, you see empty pixels on the screen. So that would be an example of where you'd have noise inserted into your signals. So let's see. Binary number system. Typical decimal number system goes from 0 to 9. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we begin again, 0 to 9, least significant bit, right? Binary number system is based on powers of 2, 0, and 1. Again, in order to design and understand these systems, we need to understand the binary number system. And so we study a little bit of binary number system, and then we get into the logic circuits. Okay. Decimal number systems are based on powers to 10, so 0 to 9, of course. And then all the standard rules still apply. You have the least significant bit, you have the most significant bit. You have each bit can store data, like 1 unit of data. And the data could have a value of 0 or 1, right? Even if it has a value of 0, it still has meaning, right? And bit is represented with the lowercase b. 8 bits together make up 1 byte, and 1 byte is uppercase B. Okay. We can go back and forth between the binary and the decimal number system by using our standard rules. So if we are going from binary to decimal, we use powers of 2. If you're going from decimal to binary, that's the example above. So let's take a look at this first. We are almost out of time. So if you have to leave, you can feel free to leave. I'm just going to cover this example before I end. Okay. So let's say we had 1101. You got 1101 as our binary number, and we want to find the decimal number. Well, we are going from binary to decimal, so we use powers of 2. So we start with the least significant bit, which is right here. 1 into 2 raised to 0, 0 into 2 raised to 1, 1 into 2 raised to 2, and then 1 into 2 raised to 3. That gives us 8, 4, 0, and 1. 8, 4, 0, and 1. You add it up, you get 13. On the other side, you have 0.1 and 0.01. So 0.1 would be 1 into 2 raised to minus 1, and 0.01 would be 1 into 2 raised to minus 2. That gives us 0.5 and 0.25, which results in 0.75. So 1101.11 is in decimal 13.75. Okay. And then the opposite, if you want to go from decimal to binary, sorry, 201. Okay. We have the base 10. And so the base 10, we're going to split this up. We are going to take 1, 1, 0, 1, 1, 1. 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3. That's our multiplier. Okay. And then here is 10 raised to minus 1, 10 raised to minus 2. That gives us 1,000. Well, actually not 1,000, but 1,000 plus 100 plus 0 plus 1 plus 0.1 and plus 0.01. And that gives us 1101.11. Okay. And there is the table on the next page, but let's cover that on Monday. Right. So we'll end class here. If you have any questions, send me an email, get in touch. Be more than happy to answer. Monday quiz, and don't forget this Friday quiz today. Okay.